Then reliability analysis tool. So this is what Ansys Sherlock is. So Ansys Sherlock is a specialized tool for PCB reliability analysis. So I think later after my session, my colleague Naveen will be providing more details about it. I think he will be also doing a simple demo. So we will focus mainly on mechanical reliability. Okay. So normally electronic applications are quite challenging in terms of simulation because of the number of parts involved, or the size or the complexity of the parts. We have a lot of small entities like traces or vias. So all this adds to the complexity of the analysis, of the modeling, I would say, and also the material behavior. So it is just no longer a normal, simple elastic behavior. So we have the material behavior it can be complex as well. Like for example, creep. So because because of the nature of the material, like the solder, and also the condition, it undergoes thermal cycling or thermal loads. So it leads to creep kind of effects. So creep is time and temperature effect on the object. Right? So this are complex material behavior. So it is no longer a linear behavior. Okay, so this kind of non-linear material behaviors needs to be evaluated or studied to understand the details of your design, right? Then physics complexity, as we saw in the previous slide, it no longer involves a single physics. It is more of a multi-physics. And if you look at the overall reliability, you also have to understand all these individual aspects like shock or vibration, drop, or maybe thermal, humidity. So all these are different aspects or the physics that you might want to look at. Okay. So best-in-class modeling methods. So we have different methods for you to understand the physics of your model or the performance. So we have very simple modeling methods like homogenized or lumped model approach, which you can just use a unified layer and define some approximate properties and do a simulation. Or if you wish to do a more detailed analysis, for example, we can also import traces from your ECAD file. So you can import the copper traces, the small traces, even less than like in terms of the element size, maybe in mm or in micrometers. Then you'll be able to do a detailed thermal or vibration analysis or structural analysis with the imported trace. Now we have also started using reinforcement elements. So these are new elements starting from this version for from last year's version for electronics applications. So we can use reinforcement elements, so they are more effective and more accurate in modeling the traces. Okay, so these are relatively new methods in Ansys for modeling electronics applications. So we have simple methods to more detailed methods for you to define the design in analysis. So this is the gist of the overall mechanical reliability analysis. So starting with the solder reflow analysis. So probably in solder reflow, we'll be mostly looking at warpage, okay, the deflection due to the CTE. Then we have tumble test, which is done using Ansys Motion, which is a rigid body dynamics tool that you can look at the dynamic aspects of the system, of the component. Then we have shock and vibration. So shock and vibration involves modal analysis or random vibration analysis, depending upon your requirements. So later we will cover all these topics in detail. Then we have fatigue and fracture. So fatigue is basically in electronics, we will be mostly looking at the solder joint reliability, SJR analysis, and fracture, like kind of delamination analysis. So all these can be also studied. Then we have moisture simulation and drop test. So this slide gives the overall picture of the mechanical reliability analysis that can be carried out under Ansys. This is an example of a solder reflow analysis. So the first, the video here is done using Fluent on the reflow process, because this reflow process happens at a high temperature, and this can lead to a lot of deformation due to thermomechanical effects. Basically, it's due to the CTE, coefficient of thermal expansion. So when you have two different materials with different CTEs bonded together, when there is a temperature load, so both will expand at different rates. So this expansion will lead to stresses at the interface, shear stresses, and this can even delaminate or fail the structure, right? So this kind of warpage or reflow, solder reflow analysis in mechanical helps you to identify this kind of interface stresses and also the overall warpage in your model. Then dynamics, so electronics reliability using dynamic methods. So in numerical methods, we have some types of numerical algorithms. One is implicit method, the other one is explicit method. So when we talk about all the vibration analysis like modal or random vibration, all these are implicit methods. And in another explicit method, normally we'll be looking at like very fast or short duration, highly transient, nonlinear kind of analysis. So mostly like a drop test analysis. Okay. So for electronics reliability, we'll be making use of both implicit methods and explicit methods depending upon the application. So first is modal analysis. So shock and vibration. So if you are interested in checking the natural frequency modes of the PCB, for example, you can use modal analysis in Ansys to understand the mode shapes. Okay? So to improve the accuracy, as mentioned, right, we can also incorporate the trace mapping features. So you'll be able to import the traces into it, and you can understand how the frequency or the natural frequency is shifting due to the changes in the material property. Then we have random vibration analysis. So random vibration analysis is also common for electronics applications. Normally, if the component or the PCB is subjected to a random vibration scenario, maybe like in an aircraft or maybe in a vehicle. So in order to represent the vibrations in an aircraft or maybe in a vehicle, we represent it using PSD spectrums, power spectral density spectrums. Okay. So this random vibration analysis is specifically designed to take in this PSD spectrum. Okay. So you can define the PSD spectrum in random vibration analysis, and you'll be able to understand the behavior. Behavior basically means stresses or deformation due to vibration in the PCB or any of your components. Okay. And we also have additional methods to understand the fatigue of vibration on the PCB components. Okay, drop and impact. So drop test is a highly nonlinear and time domain simulation. Okay, so normally drop test happens for a fraction of a second, and it involves fracture, failure, delamination of materials. Right? So this kind of extreme deformation scenarios can be handled only using explicit solvers. So in Ansys, we have Ansys LS Dyna, which is one of the most powerful explicit solvers that can easily handle all these types of behaviors like delamination, fracture, failure, failing of a contact. All these aspects that happens in a drop test can be easily simulated using Ansys LS Dyna. Then we have moisture effects. So moisture effect is part of Ansys mechanical solution itself. So when the moisture is absorbed by the component and when you heat it up, it will lead to failures, right? Or stresses, hygroscopic stresses. So all this comes under the diffusion analysis method in Ansys. So we are using again a coupled physics approach for it. So we can do a structural diffusion analysis or thermal diffusion analysis or structural and thermal diffusion analysis together. Okay. So to understand the aspects of moisture diffusion and the stresses. So this is part of Ansys mechanical. Then we have fatigue, vibration fatigue, and fracture. Okay. So under fracture mechanics, we also have a few applications for electronics. Okay. So one is delamination simulation. Okay. So if you wish to simulate delamination or debonding of contact along a predefined path, we can use the delamination capabilities in Ansys mechanical. This is under Ansys mechanical fracture mechanics. So this will be able to simulate the delamination. Okay. So it can be due to any type of loading. Then we have vibration fatigue. So vibration fatigue is mainly due to vibration, the PSD spectrum, for example. And we have dedicated options like under the fatigue tool to calculate vibration fatigue for electronics components. So with this, you'll be able to understand the fatigue life as well after doing a vibration analysis like random vibration or harmonic analysis. Then we have our traditional method of calculating the reliability, which is using the advanced material models like Anand viscoplastic model. And then we calculate the creep strains, and based on the creep strains, we will be able to calculate the solder joint fatigue life. So we have some examples here. Trace import. So trace import can be a very detailed modeling. So you can import traces for each layers, and you'll be able to view the trace information for each layer. And after importing those traces, so we also support shell modeling, because CAD solid modeling can be challenging. So we also support shell modeling for trace mapping. Okay, so you just need a single shell to import the traces. Then after importing the traces, you can do a thermal analysis, or maybe structural analysis, warp-based analysis, or even a modal analysis. So all types of analysis are supported. Then we have we have options to import thermal loads from ice pack and apply it as a boundary condition, because when we have thermal loads, the thermal loads will start the expansion of the components, right? So due to this, there'll be interface stresses, right? So this can be studied by applying the thermal load from ice pack and studying the mechanical aspect of it. Yeah, so the same. So this is a warp-based analysis by using temperature. So temperature load can be from ice pack, or it can be also from Ansys mechanical. And these are the interface stresses, shear stresses. Then we have this delamination. So I mentioned for delamination, we have few methods: contact debonding method or delamination interface delamination method. So in this example, we have a contact region. So this contact region can be set as a debonding region. So means the stress. So we have to define the criteria, and once the limit is reached, then the nodes will be released, and the thing will start to the deform. Okay, so we can see some pictures here. Next is solder analysis. So yeah, you can see you'll be able to observe the stresses, stress distribution, or the deformation of the solder joint, and you can apply a thermal cyclic loading. And yeah, and we also have an add-on tool called this ACT, solder joint fatigue ACT. So this solder joint fatigue ACT will be able to calculate the fatigue life. Okay. So how this method works is we'll calculate the creep strains for 3 or 4 cycles, and based on the creep strain accumulation or the damage, the method, the solder joint reliability, so solder joint fatigue ACT will calculate the fatigue life and the number of cycles to failure. So for solder life prediction, the assumptions are made. So on crack initiation propagation. So we don't model the crack in a solder joint reliability analysis. So we model the solder using some advanced material model, usually Anand viscoplastic model. Okay. Then we will calculate the plastic work or the creep strain accumulated per cycle or per thermal cycle. And using this damage, we have a simple method to predict to calculate the life, number of cycles to failure, or the life of the solder joint. So this is the process. So we have this Anand viscoplastic model, which is the commonly used model for this application. So you can find a lot of papers on it. And then we use the creep strain energy density and use this Darboux method. So this is a commonly used method, analytical method, to calculate the solder joint fatigue simulation or the solder life prediction analysis for electronic components. Okay. So we'll take the output from Ansys and we just put it here, and you'll be able to obtain the life. Then if you wish to look at the details of analysis portions, we also offer a technique called submodeling. So submodeling allows you to focus on a specific region. For example, if you wish to look at a specific individual solder ball with more details, first we can do a simple model, simple global model. Okay. Okay, so you can model all the components, but with more approximations, okay, with less details. Okay, then you apply the actual loadings and then find out the stresses or deformation, and then focus on the area. Right? So when you focus on a submodel, you just focus on a small region and include all the details, all the necessary details. Okay? So in the submodel level, you'll be able to define almost all the details, and then you can transfer the conditions from a global model to the submodel. The program will automatically transfer the conditions. Okay? Then you can do the analysis of the submodel alone to get more accurate results of the small region. So this is called submodeling technique. Okay, so yeah, so mechanical reliability analysis helps to address almost all these reliability issues, starting from thermal aspects, warpage, solder reflow, drop test, impact test, or tumble test, vibration fatigue, modal analysis aspects. So you will be able to, it's like a comprehensive solution for you to understand all the mechanical reliability issues related to the PCB or electronic components. So we have a very strong pre and post-processing techniques. We have robust workflows, and we have thought of automations like the ACT, for example, to study the solder joint reliability, or the submodeling method to improve the accuracy of the model. Okay. So we have different methods and also workflows for you to study these different aspects. Okay. And then comprehensive multi-physics. As mentioned, we can also couple multiple physics solutions in Ansys. Maybe you can start from Sherlock, then later you can transfer the model to ISPAC for a thermal analysis, or you can from Sherlock you can transfer the model to mechanical for a vibration analysis, or you can transfer the model from SI wave to ISPAC for thermal analysis. So we also have cases where customers use electrothermal and mechanical simulations. So where they start with electrical tools, and then they'll transfer the loads to ISPAC for thermal analysis. And once the thermal analysis is completed, they will transfer it to ISPAC for warpage analysis. So we have a robust workflow for even a multi-physics solution involving more than 2 physics. Example here. And then if you wish to look at the details, you can further do a submodeling in a localized region to understand the stresses or maybe the creep strains. Then optimization. So optimization is also another aspect of reliability. So we have dedicated tools for optimization. So we have 2 tools, Ansys Design Explorer and OptiSlang. OptiSlang is one of the most powerful tools in the market for optimization studies. Okay, so basically Ansys allows you to set parameters in your models in mechanical or ISPAC or SI wave, whatever you are using, and then you can define a DOE, design of experiments table, so where you can set a range of values for all the input parameters, and then based on this range, the program is able to identify or relate the parameters, input or output parameters. Then using this relationship, you can optimize. So you can set a goal. So you want to say, you can say the warpage must be less than 1.5 mm, for example. So you can set this kind of goals, and the program will calculate back the required input parameters to achieve this goal. Okay. So this is an example of optimization process in electronics reliability study. Yeah, I think that should be all from me. And now I'll transfer it to my colleague Naveen. And later, if you have any questions, you can just ask me after the session.
Thanks,
Naveen?
Let me share my screen. Okay, I hope everyone can see my screen.
Yes, can.
Okay, good afternoon, everyone. My name is Naveen. I'm going to present on the Sherlock portion. So Sherlock is the tool used for reliability for printed circuit boards. So the following slide, I'll show how it differs from the reliability analysis that you do inside. And this is a mechanical bench. So first, a little background on reliability challenges. So normally, when we are developing an electronic product, so an electronic product obviously consists of an enclosure and many devices, and of course, most importantly, a printed circuit board assembly. So normally, the typical stages is to design and then build, and then manufacture, and then test, and then if the reliability goal is not met, so you need to do fixing and then retest again. So it's a cycle. So usually this cycle that you do several times, it consumes money, so and also resources. So by using simulation to perform a reliability study, we can reduce the number of cycles that we do for reliability studies. Okay, so normally in the design world, normally what is done is we use traditional CAE tools. Okay, so Ansys or Nastran or Abacus. So we usually use those simulation tools to calculate the stresses in your printed circuit board, but it does not tell you the reliability. Okay, so the lifespan of the product, for instance, the solder joint failure, what is the lifespan for it? So it's very difficult to predict all these kind of reliability metrics. So that's where Sherlock comes in. So what Sherlock is able to do is to take all the stress values from any CAE analysis and then give you some meaningful reliability analysis. Okay, so reliability for thermal cycle fatigue, solder reflow, and vibration and mechanical shock. These are examples of few analysis that can be done inside Sherlock. Okay, so we have a PCB and then we have many different type of components soldered on top, and then we also have an enclosure. Okay, that includes the board within. So we can do a full system level analysis inside Sherlock. Okay, so usually when we want to do a reliability analysis, we have a metric. Okay, so we have a lifespan that we can set. Okay, for the lifetime and also the probability of failure. Okay, so this is the baseline that we set. So Sherlock is able to predict for all the different type of reliability failures, what is the metric of the reliability. Okay, so does it fail before the 10 years lifespan, or before the 10 years the reliability probability goes up to beyond 10%. So these are the type of studies that we can do inside Sherlock. Okay, so basically what Sherlock does is it imports a ECAD file. So famous, well-known 3D layout, PCB layout tools like Mentor and Cadence and Zuken. So you can bring in the ECAD file, and then you can assign component properties and material properties for the laminate of the PCB and the copper. And then you can calculate the stresses using the APDL solver in the background. So it can give you a reliability results for temperature, stress, and strain. Okay, so basically Sherlock has a big library of all the different components mounted on the board. Okay, so discrete components, all the different ICs, so all the different type of components, the libraries will be inside the Sherlock. So we can immediately assign them after importing the ECAD file. Okay, so once we've imported and assigned the libraries to the board, so we can bring this exported board to all the different Ansys tools that we have. So for doing further analysis for power and signal integrity, so we can use Ansys SI wave and HFSS to do the analysis. And then you can also use export the ECAD file to do a thermal analysis using ISPAC. And then you can also do stress analysis using the Ansys mechanical also. Okay, so once the ECAD file has been imported inside Sherlock, we can export it to Workbench. So the main purpose of this export is, let's say, inside Sherlock, we got some reliability analysis for mechanical shock or for some vibration. Of course, ECAD file is just a 2D file. Okay, so sometimes you have an enclosure. Enclosure is a 3D file, so we can't analyze 3D elements inside Sherlock. So that is why we need to export this ECAD model to mechanical, to Workbench, and then we import the 3D CAD of the enclosure and then contain it inside, and then have the board inside the enclosure, and then we can do some further mechanical stress analysis, and then we can bring back the analysis to see how the reliability changes for the vibration studies and the mechanical shock analysis that is done inside Sherlock. So that is the purpose of doing this Sherlock to workbench integration. Another purpose is for trace reinforcement. So usually in a PCB board, you have all the traces and copper spread all over the board. So when we want to do a thermal stress analysis, it's important to consider the copper traces. So we can do something called trace reinforcement. So we can bring the model from Sherlock in mechanical and then do a thermal stress analysis by using the trace reinforcement. Okay. So usually in the first step in designing a PCB board, we need to do an initial board outline. Okay, so we need to define the board outline, and then we need to select the parts that are going to be used. Okay, so we have a bill of materials. So when we do a reliability study, so usually different components have different properties that affect the reliability. So we can do an assessment to choose the right components from different component manufacturers on which parts are suitable to be mounted on the board. And then so by doing this analysis, so we can consolidate a bill of materials listing of the parts that are best candidates to meet our reliability metrics. And also sometimes you have change management. So sometimes certain parts go obsolete, so you need to find a replacement part. So when you want to see whether a replacement part meets a reliability metrics, so we can do that type of analysis inside Sherlock as well. Okay, so on a broader view, so usually when it comes to printed board, circuit board, usually we have a design team, and then we have a mechanical team, and then we have manufacturing, and then we have testing. So these are all different departments that do the reliability studies differently. Okay, so you have 4 different silos that manage the reliability. So by having Sherlock, we can have all these different disciplines come together on one platform to ensure the reliability of the PCBA is met. Okay, so here's a case study of ECU board. Okay, so ECU used in automotive applications. So normally when we design a board, we place the outline of the board, we define, and then we add the connectors and jacks. Okay, so those are placed over here. Okay, and then next we have to place the IC device. Okay, so you have integrated circuits, you have all the sensitive electronic components that place. So we need to decide where's the best place to put the components, so that okay, we will not have a big shock issue or some vibration issues. Okay, so by doing analysis on the mechanical shock inside Sherlock, so we can see that the shock starts to fail before the 10-year mark. Okay, so at the 3-year mark, the probability is going higher and higher. So our probability base is 20%. So we're trying to meet that with a lifespan of 10 years. So it's failing before that. So we can see here is a reddish. So this component here is not a good place to place in this location. Okay, so by moving the component here, okay, so we just a single click, okay, we can just move the component here and then run a quick mechanical shock analysis inside Sherlock. So we can immediately see how the reliability is showing. So if you use a CAE tool, you need to wait for a long time to get an answer to do these different what if scenarios. So by using Sherlock, you can calculate the result in a few minutes. Then you can see how it affects your reliability. Okay, so in the next case, we don't move the IC. So we just add some supports. So you can see the reliability is improved. Okay, and then we use an underfill. So it's further improved. Okay, so this is how we do very quick analysis for reliability inside Sherlock to decide the optimal placement for the components. Okay, so by having this Sherlock, having the analysis run in a few minutes as opposed to a location for components on the PCB board. Okay, so yeah, it also, so by doing so, we can improve the reliability of the product and how it will perform in the field. Okay, so sometimes automotive and aerospace bots, when they go in the field, they tend to fail. So you have all this warranty, product recalls and all that. So we can reduce the risk for all these failures. Okay, so these are the type of analysis that you can perform inside Sherlock. So you can do fixing, modeling, natural frequency, and all these different analysis. Okay, so I've done on the PowerPoint side. So now I'll open the Sherlock software. So I'll provide a demo to give you an idea how Sherlock does the analysis. Okay, so here is the Sherlock window. Okay, so what I do is I'll open a job. So normally the first step is to import a ECAD file. So these are the popular ECAD formats that can be imported inside Sherlock. So by having this format, so we can immediately have the board imported. So if I click here, so this is your PCB board with all the components and also with the connectors, and then with also the mounting point defined also. Okay, so the mounting point, so it affects the stresses and the reliability of the board. Okay, so after we imported the board, then we need to adjust the stack up. Okay, so if you see the stack up of the board, so we need to assign the laminate material that is used inside the PCB. So we have a big library of laminates. Okay, so if I click here, so these are the different laminates that are available inside Sherlock. Okay, so basically Sherlock is a software developed by a company called DFR. So DFR does very detailed research on reliability of electronics. So they have a lot of material libraries in their database. So here they have all the material properties for common laminates used in PCBs. Okay, so you can also define your own and then put into this database as well. So in addition to laminates, we also have materials. Okay, so all the different materials properties, and then you also have solders. Okay, so different solder material. Okay, so we can add different ones as well. And then we also have parts. Okay, so these are the different parts that are inside there. Okay, so in the next step, what we need to do is we need to import the bill of material parts. Okay, so these are the parts that are going to be mounted on the PCB. So we need to assign a library to them. So Sherlock has a database of 200,000 parts, 300,000 parts library. So based on the manufacturer part number, the library will come in automatically. So in cases where the library don't come in automatically, so we can assign them manually. So we can edit parts. Okay, let's say for this IC, so we can click here and then we can choose all the common ICs that are available in the market. Okay, so you can see for 128 pins, 168 pins, all the different dimensions that are available. Okay, these are all different standards. Okay, so for 14 pin, you have all these different dimensions. So by importing this library, so automatically all these properties will be assigned to this tabs. Okay, so to do the reliability study. Okay, and then that's for the board portion. Okay, so next we need to assign the loads. Okay, the loads that the product will encounter when it goes in the field. So normally we need to define a life cycle. So for the life cycle, we need to define a metric. Okay, so the product is supposed to last, what's the lifespan of the product? So, and then the probability of failure. Okay, so it must not exceed this percentage. So we need to design. So this is the baseline value for which we want to measure the reliability against. So once we have defined that, so next we need to define the loads. So we can group them into different categories. Okay, so if I right click, so I can add all these different events. Okay, so we have a thermal event, we have harmonic, and then random. So by using this four type of events, so we can define all these different conditions. So let's say a collision. Okay, when the product being transported, it hits a pothole. So what is the vibration curve? So we can define. Okay, so based on the shock event, so we can define the duration of the shock event and then the cycles. Okay, so duty cycle per year, per day. And then we can also define the pulse profile as well. Okay, so we can define the pulse profile. So similarly, okay, for the temp cycle also can be defined. Okay, so if you edit, so here you can define the temperature cycling. Okay, and then also again we can edit the profile. Okay, ramp and then hold. So we can define the cycle. So these are the loads that we apply to the board for us to do the reliability study. Okay, so once we have defined all that, so now we can run the analysis. Okay, so once the analysis is done, so let's say for solder fatigue. Okay, so these are the type of results that you can see inside Sherlock. So it gives you a component by component. So these are a listing of all the components that are soldered on the boards. So it tells you what is the failure rate. Okay, so we can see in the live prediction here. Okay, so after the 5-year mark, it goes above. So we can see what are the components that are failing. So in red, so I can see, I can right click and I can, okay, so the live prediction curve that I see here is for all the components of the board. So if I just want to view for one component, okay, so I can right click and then view the live prediction. Okay, so I can see the live prediction. And then let's say for random wipe, okay, so I can right click. So again, I can see the results. And then I can see that one component is already failing. So the damage will be shown here, and then the time to failure, and then the probability for failure can also be shown here. Okay, and then so what I can do is I can visualize, okay, in 3D. So if I click view 3D results. Okay, so here I can see, so here is the random wipe displacement. So what I can do is I can just press refresh. Okay, so I just changed the warping. Okay, so in this case, the mounting points are defined at the edge of the board. So that's why the red zone is in the center of the board. So that we see the maximum displacement here in the center of the board. So if we add a mounting point here and here, so this thing can be alleviated. So we can see that these two components are failing because it's in the center of the board. So like that, we can do a different type of studies to assess and then see visually where the stress points and the displacement are. Okay, so we can see the strain, and we can see the component score. So we can see it in a metric form and also in a visual form. So we can see a different type of analysis for random wipe and then for solder fatigue. Now we also have thermal MAC. Okay, so thermal MAC is basically give you the, okay, normally in a board, so you have your laminate material, you have your copper, and then you have your components. So all of them have different CTE properties. So the mismatch in the CTE causes a thermal stress. Okay, so the displacement value and the strain is shown here, and then the maximum temperature also. Okay, and then also the PCB features can also affect the solder fatigue also. So if I check here, so if I go to a component, okay, so here I can define the solder that I use inside the board, and then also I can define the stencil that is used in the manufacturing process. Okay, so what is the thickness of the stencil that is being used? So stencil controls the amount of solder that is being deposited. So these are all the different parameters that you can play around to improve the reliability of the board and all the different components. So we can also adjust the size of the PCB landing, okay, to ensure that they are all correct. Okay, so we can change all the different properties. Okay, so I think that's all I have. Okay, so I think we can begin our Q&A session. So I'll give it back to you, Santhya. Thanks.
All right, thank you so much, Mr. Naveen. So do we have any questions for our presenter today? So we have about 12 minutes to become 3. So please feel free to ask any questions that you have and we can answer it while we are still here. I also dropped my email address in the chat box. So if you email us. And also, I would like to tell that today we, for this participation, we will provide a certificate on the participation, so you can get it with along with the by scanning a QR code. Just give me a moment. I'll take out the QR code.
Naveen, there is a question. Does this software works only for ICs or
only PCBs? So
ICs
okay,
or
so
only PCBs?
yeah, basically Sherlock is meant to analyze a printed circuit board assembly. So that means we have a printed circuit board, and then we also have components that are soldered on the board. So basically, what we are doing is we are doing a study, let's say for vibration or mechanical shock. So the result that we see basically when there's too much vibration or the shock is too great. So basically, what we identify as a failure is when the solder joint detaches. Okay, so that is classified as a failure. So we're doing that type of study. So I would say is mainly on a PCB level. Yeah, PCB with a component soldered on the board. Hope that answers your question.
Okay. Thank you so much for the question. Thank you for explaining.
And I think, Santhya, some people are asking for a presentation. So, so when you fill the feedback form, you just mention this, then we'll be able to send the presentation slides to you.
Yes. If you scan this QR code, there will be a feedback form that will be appearing, and then also I am dropping the link for that, so you can share. Oh, wait. No, sorry. It's this QR code. I'm so sorry. It's this one. Yeah, and then you can claim your certificate as well, and then you can just write it in the form itself, requesting for the webinar record, and we will pass it to you as well. Okay. And also, to keep yourself updated with more webinars, more upcoming webinars. So you can find our name in LinkedIn as well. So yeah, if there is any more questions, if there is no more questions, then we still have 7 minutes though, so we can wait. There's one question here. Would there be any difference in setup on these two different Ansys version? Mr. Hari or Navin?
Okay, friends. Okay, so the workflow remains the same. It's almost the same workflow, but you might get new options or more options in the latest version. But the workflow will still remain the same. So there is no change in the workflow or the methods that we use. Just that we have additional options in the latest version.
Thank you, Mr. Hari. Mr. Jeremias, I hope it answered. Do you have any other further questions? Okay. No more questions, then maybe we can end it 5 minutes earlier today. So thank you so much everyone for joining. Thank you for giving us 55 minutes of your time. I hope it was a good session for you all. So if you have any other further questions, feel free to email us to our general email, as well as you can email me and I can find for you the right person to answer your questions. And then please follow the last link that I sent in the chat box to fill the feedback form. It will be really helpful for us to improve in ways in the next webinars. And yeah, you can also scan this QR code. It's an easier way to fill up. Okay, thank you so much for joining. Bye. Thank you, presenters.
Thank you. Thanks, Cynthia. Thank you. Bye.
Thanks, Santya. Bye.